So in this video, we're going to cover the second method for approximate trusses, and that is when members can carry both compression and tension forces. So here we have roughly the same truss as we did last time, same 20 feet for every single direction horizontally and vertically, but this time 15 kips loaded on all four of the top joints E through H, and then a 7.5 kip force going horizontally at E. Again, we want to find forces at E. After that, you could obviously do the same thing throughout the entire truss, but since E is the most complicated joint, we're going to start there. So step number one that we want to probably do is, obviously we're going to want to make a cut at this spot. And if we're going to do that, we probably also want to find the vertical force here at D, so dy. And in order to find that vertical force over at dy, we're going to sum the moments at A and set it equal to 0, taking my favorite counterclockwise to be positive. So since the 15 kip at H acts directly in line with A, he's not going to be a part of our equation. So we're picking up at joint G, we have that 15 kip force, and he is going, of course, down, so he's going to be going this way around A, and that's going to be negative. So again, that's negative 15 times a distance of 20 feet. Then at joint F, we have the same thing, minus 15, except his distance is 40 feet. At joint E, same thing, minus 15 kips times a distance of 60 feet. Then we have the joint E, he's going to be going that way, also negative, so we also have negative 7.5 kips times the distance of vertical, 20 feet. Lastly, we have dy, and dy is going to be going this way around A. So for once, something positive, so plus dy times his distance of 60. So dy is going to equal 32.5 kips. Wonderful. So with that information, let's go ahead and draw our free body diagram for the cut. So we have our vertical member, we have a horizontal member at each end, and we also have a diagonal member at each end as well. At the top, 15 kips going down, 7.5 kips going sideways. Again, we just found dy. He is 32.5. Adding in all of our forces, we have our horizontal at the bottom here. This is force CD. Then also at joint D here, going up, this is force DF. Technically, inside of this guy, though not drawn out, is force DE. Same thing, technically he's here, force DE, even though we haven't broken him out yet, right? We haven't made the cut, so he's not really there. But he is one we want to find. The diagonal here is FCE, and at the top, this is FEF. So this time, since none of the members are slender and they can all hold compression force, we kind of expect that they're probably going to have compression force, not necessarily all of them, that some of them can. So the first thing we want to look at is we have only members DF and CE here carrying vertical force, right? Since DE, he's not actually here, he's made up. So if we were to sum the forces in the y direction for this cut, we have FCE. We also have FDF. Now we don't necessarily know their direction, but we do know that we have those two unknown forces. What we also have is a negative 15 for the load at the top at joint E, and we also have a positive 32.5 from dy. So all of that equals 0. So what we want to find is what the forces FCE and DF are going to do. And with this method, we assume that they're each going to carry half. Well, half of what? That's a good question. We're needing to find this value right here. So 32.5 minus 15 is actually going to be 17.5 vertical, right? Negative was down, so this is going to be a vertical force. So between the two of them, FCE and FDF, they need to carry 17.5 going up. So because they're all on that side, they actually, since this is going up, we actually need to flip them since it is a little bit too much, and we need them to go down. Right, both of these guys need to go down because the 17.5 is going up. So we have to counteract this in order for it to stay equal to 0 over here. So we're going to have downward force, but again, that force for each of them is going to equal half of 17.5 going down, which is 8.75 kips. So again, each of them is going to be 8.75 kips down. So if we come over here and just draw a little down arrow, right, he's going to be going down, and again, this guy's going to also be going down. Now, if we're looking at our forces, again, kind of ignore what's going on over here. Ignore those arrows that we drew previously. If it's going down for this the joint here at D, so this is going to be DF. If it's going down, then he's also got to be going into this member to create a grand compression force, actually, right? I have to pick one direction. It's got to go in this diagonal, so this diagonal is therefore going to go down. And at the one at joint E, if he's going down, then he's going to have this grand total downward facing guy, so he's going to be in tension, actually, so he's going to also have horizontal that way. And remember that this vertical force is 8.75. Right, we have that. So that is actually the directions for F, DF, and FCE. So now we kind of need to go back and remember that our truss here is 20 wide by 20 tall. So what we need to do is kind of find, if this is the vertical component, then we need to find what the horizontal component is. So say for FCE, FCE is going like this, right? This is FCE. So he has a vertical component going down and a horizontal component going over. So the vertical component is 8.75. We're going to kind of use like similar triangles here. We have a total distance of 20 feet horizontally, 20 feet vertically, and this is technically 20 times the square root of 2. So we can kind of use similar triangles here. And I'm going to pick a really easy one. I'm going to try and say solve for this x value instead, because the height and the width here are the same. So 8.75, the value of that force, right? That value of that force, how does it relate to the x force value, if we're saying in kips here? What's the size of the x force? Well, the height of the triangle is 20, so these two are related, and then we're also a width of 20. So these two are related. Well, that equals 1, right? Over here, 20 over 20 is 1. So our x force value, so the horizontal component of FCE, the horizontal component of it is also 8.75. So if I want, I can find FCE as a total by just using Pythagorean theorem here, right? If I want to find the resultant, it's the same way you would find the length of the triangle side. So we have 8.75 squared plus 8.75 squared, all under that square root there, right? Because we have a squared plus b squared equals c squared. So if I just take the square root of it, then I'll find it. So FCE is actually going to be equal to 12.4 kips. Now the question is tension or compression. Well, let's go back and look he's going out of the member, so he's going to be going that way, and he's in tension. It's the exact same triangle for FDF. So FDF is also equal to 12.4 kips, but he's going this way, if you go back and look at that picture, which makes him actually in compression, which is not really a problem because, again, he's not a slender member. He can actually hold compressive force. So now that I'm looking at this, I've got FDF, and that is 12.4. I've got FCE, which is 12.4. And I've got two horizontal forces here. And so I'm going to want to solve for one of them. Well, if I want to solve for one, I'm probably going to sum the moments about one of these two joints. And honestly, E looks like a worse joint to leave open. So I'm going to sum the moments about joint E. So if we sum the moments about joint E and set it equal to 0, thankfully all of this kind of goes away, right? None of that actually exists in our moment equation. And neither does the 8.75 vertically. And don't forget that the horizontal component, which we found, was also 8.75. So we've actually, and 32.5 also doesn't act in it either. So we've only actually got two forces acting in the direction to cause a moment. We have the 8.75 times the distance of 20 feet, and he's going to be going that way, which is going to actually be positive. And then we have FCD, who's going to be going that way, who's going to be negative. So minus FCD times also 20 feet. So this really doesn't take rocket science to figure out, but FCD is thus 8.75 kips. And yeah, he's going to be going in his tension direction. So cool. So now that we have that, the last thing that we can do here, if we have our force of 8.75 kips for FCD, looking at our wonderful, wonderful free body diagram here, what we can do is simply sum those forces in the horizontal direction, because the only guy that we don't actually know at this point is EF. Right, so if we actually go in here and sum the forces in the x direction and set it equal to 0, again we have the 7.5 from the applied load in the positive direction. We have minus FEF, and we have the horizontal components are all the same, right? So FCE is also minus 8.75, and that's FCE's component horizontally. Then we have plus 8.75, and this is FDF's horizontal component. Right, so we covered this one here and this one over here. And the other x direction force we have is FCD. So we need to subtract, which we just found him to be 8.75, so minus 8.75, and this is FCD. So that's a lot of 8.75s. Conveniently, two of those 8.75s cancel out, and we're going to be left with FEF being a negative 1.25 kips. So he's actually a 1.25 kip compression force. So we found all four of those forces that we wanted to know, but we haven't yet found FDE. So what we can do now is go to, I like to do joint D. I think it's a little bit simpler. So for joint D, he's going to be just a little vertical, a little horizontal, and a little diagonal here. We're going to have FDE going up, and again we've got 32.5 for dy, and then we just found all of these forces. So I'm going to go ahead and write in the vertical horizontal components. Right, remember that this is 8.75 horizontal and 8.75 vertical. And I mean, technically FCD was also 8.75. So the sum of the forces in the x direction, yeah, he still works out. But the sum of the forces in the y is going to find us what FDE is. So FDE is positive. We have the minus 8.75 vertical, and then we have plus 32.5 vertical for dy. All that equals 0. And we get that FDE is equal to negative, so that 32.5 is pretty massive, negative 23.8 kips. So that's 23.8 kips in compression. And that's all of our forces at joint E. So really not that bad. Again, the big thing that's different here with method 2 is the fact that each one of these forces is going to take half of that overall. That's the big assumption that we're making with our method 2. So it's really not too terrible.